Okay, eddy current 1, a little bit about machines here. What you're looking at is a Nortec 500D we bought from Olympus. Basic stuff here. What we've got hooked up is a Nortec 1 to 500 kilohertz probe. Okay, and if we unplug this thing, let's just turn it off just for fun. Okay, turn it back on. I unplug the probe. Okay, so when this thing comes up, you'll see what happens here. You can tell the screen's kind of dirty. Give it a second to boot up. Alright. So now we have just a regular screen. So now let's plug in the cord, plug in the probe. Okay, it's got a little chip in it and it takes us to a known screen. So it says model 9222. See, 1, 2, 3, 4, 2's 02. 1, 2, 3, 4's 02. See part number there? That's what we're talking about. And then it's got a serial number as well. We know it's eddy current. Let's push log to verify. Okay. So it's linking us. Tells us what kind of probe it is. We hit main. Now we're at a screen. Okay. I'm pushing. Let's back out of here a little bit. There we go. I'm going to push the setup button. I want to go to special settings and colors. Make it easier for you to see on the screen here is what I'm trying to do. I think that's probably about the best, the dark green. That's hard to see. There we go. We'll keep it at the dark green. So, there I am. You can see my reflection in the background there. Okay, so now you can see me. So we're looking at the screen here. If we were just looking at a basic eddy current screen, what we would be looking at is this. Okay, if we start over here at 0, we could put any kind of number along the bottom of this screen. We start here again at 0, we could put any kind of number along the side of the screen. But like we have up there, okay, from the calculations we were looking at, we have the impedance plane diagram. Okay, and on that impedance plane diagram, we have resistance along the bottom, inductive reactance along the side. All of these points out here would be an impedance point. So I'm going to erase all those points and push null. Okay? Just because of where it's set up, my flying dot goes back to the center. But let's move that flying dot. So I'm going to push display, screen setup. This lets me change my dot position anywhere I want it along the screen. Okay? I can just draw about anything I want here. Kind of like a fancy Etch-a-Sketch. But we're not going to do that. So let's erase it. Now if I push null, it's over here. Well, that's because I've got it at 29 and 69, or 30 and 70 basically. So let's run them back to 50 and 50. Okay, push null. There we are, back to the center. Let's go back to our main screen. Frequency 1's where we're going to spend most of our time. Okay, we've got a frequency of 200 kilohertz, an angle of 0, and then a couple of gains here. We want to put these gains at about 50 or so a piece, but we want them equal for right now. Okay, once you've got them where you want them, okay, it doesn't matter if they're spread apart or they're the same or whatever. You push this gain button, you can run them both together. Okay, so we're going to park them both at about 50 there. Alright, so we're looking at that. Let's just take our probe and touch it to this piece of ferrite over here. Okay, so let's back out so you can see that. Okay, there we are. Let's just touch this piece of ferrite. Let's null again. Okay, if you can see, I haven't quite touched it yet. Getting closer, getting closer. At some point, about right there, the dot starts to move. That is liftoff. Okay? So there I've touched the piece. There's titanium. Oops. 304 stainless, copper, nickel, magnesium, aluminum. Get out of the way so you can see it. Aluminum. We want this thing to be rotated, at least I do, because that's how I run them. Well, I want my ferrite to be pointed straight up. So I'm going to tap on my ferrite here, push the angle button or the rotation, and rotate this thing straight up. Okay? So I'm going to erase again. Now I'm going straight up. There we go again. So that's a conductivity curve. But let's take our gain and go to 57. Somewhere around 57. Okay? Erase. Null. So it's gotten bigger. Increased the gain, we amplified the signals, now it's bigger. Pretty simple, right? So let's take our gain down. Let's run them down to about 40. As you can imagine, that signal or bunch of signals ought to get a lot smaller. Which it does. Okay? So we're for 200 kilohertz, about 50 dB is about where we want to be for this setup. Now there's other things that we can do to change that, but for now 50 dB is giving us just about our best signals. Okay, you can see how they're all a lot longer there. So let's erase and get rid of the old stuff. And you can see how instantaneous that is. That's very, very instantaneous. So for all intents and purposes, we talk about all the inductive reactance stuff and all that. You read about it. It says there's a lag and there's time and all this time's involved, but all that stuff is in microseconds, nanoseconds. So when we touch our probe to the part here, it's pretty much an instantaneous change. Okay? And that all comes from the impedance of the coil. We're just picking up the differences in the impedance of that coil and where it came from. Okay? So that's a conductivity curve. We could sort alloys just looking at magnetic versus non-magnetic. So if I'm just going to touch this table here, the underside of this table, which should be steel, okay, which it is, that's what it's telling me. So let me touch my watch, hopefully it's not fake. Okay, that part of my watch is stainless steel. Alright, that part of my watch is pretty close to stainless steel. I must have a cheap watch. That's okay. I didn't need an expensive one anyways. So, let's look at that compared to stainless steel. There's 304 stainless. There's copper nickel. Okay, so if I touch my watch, I think I'm going to fall in the middle there. Close to copper nickel. Okay, yeah, so maybe I've got a copper nickel watch. I mean, ring. I highly doubt that. But these are just some of the reference materials we have. Okay? So titanium, 304, copper nickel. These two look pretty close, but I can guarantee you if we spent some time and separated them out, you would see that they were very different. So let's transition from there over to a crack detection. Okay, surface crack detection, just so you can get an introduction to eddy current. Let's take our dot and move it down here by pushing the setup button. Whoops, setup. Sorry, display, screen setup, that's where I was going. And go to 90. Push the right buttons. And then down to 10. And that's going to park us down here in the bottom right corner. So we're going to erase it. Going to null. That's going to put us there in the bottom right corner. And if we touch the ferrite, we haven't changed how our signals would look. We've just moved where they're located. Okay, and that's alright. That's not a bad thing. But we want to be able to tell if there's cracks in this aluminum standard here, which we already know that there are. So we want to be able to null on our material. Okay, and that's going to park us here in the center at our 90 and 10, but you see if I wobble the probe, I get a different reading. Okay, this really isn't the right way to do this, but I realize that. I'm just holding this. Okay, because you should be able to see a difference. If I touch this now, see it's going to a different spot because my finger was on there last time. So let's null it. Okay, so I lift up. There's good material. There's air. So let's rotate that by pushing main, frequency 1, and we're just going to tap on this. Okay, so as I tap on it, change the angle, that is. Here we go. So I lift up, everything's going back to the left. Renull. There we are. I'm going to give this some more gain. Run it up to about 54. I'm going to renull. Go up to about 56. Because I want to stretch this across the bottom of my screen here. That's what I'm doing. That's a little too much. It's temperamental. Can you notice each time I'm renulling? That'll work. So we're pretty much all the way across the bottom of our screen there. If we run over these cracks, there they are. Let's roll this up a little bit. Let's put some more vertical gain in it. So I'm going to put that at about 67. It's about 10 dB higher. Okay, so I'm going to renull. Alright, so there we are again. You see how it's got a bigger hook on it now. Comes down and it's got a bigger hook on it. So we start over here at the 8,000ths. Okay, scan across the 8,000ths. Okay, pretty big signal. There's our 20,000 signal. Now it's walking across the bottom of the screen here because I'm walking the probe. So 20,000ths and then 40,000ths is bigger yet. Okay, let's erase all that. Renull. Do that again. 8,000ths, 20,000ths, 40,000ths. So you can see now more how they are rotated up instead of laying flat against the bottom. And that's a good thing. We want to see that. That's just telling us, hey, we've got different size cracks in this aluminum block here. So for now, just getting you oriented to an eddy current machine, getting you to understand the possibility of, hey, we can use this for conductivity or alloy sorting and defect detection on the surface is where we're headed for this week. Next week, we're going to look at some of the actual labs, how the labs work, how can we relate the labs to the theory, because some of that stuff is a little bit different. So really, if you're looking at this, you don't say, well, inductive reactance, I don't really know about inductive reactance there, or Ohm's law, or something like that. So just getting used to seeing an eddy current scope, getting used to seeing what it looks like. We're going to take some time next week and look at how everything relates together and then take a look at some of the labs to see where they actually are coming from. So just soak it in today or soak it in this week, and the next week we're going to press on with actually making that tell us something. Okay? So let that soak in and we will see you next week.